This is the first lesson in the forces topic of the GCSE physics program. So today we're going to look at scalars, vectors, contact and non-contact forces, and really after this little video you should be able to talk about these four things confidently and give some examples for each, and at the end do some vector diagrams. So straight in there, scalar quantities, what are they? Well, scalar quantities have magnitude, so size is another word for magnitude. They have an amount, a quantity, which describes their magnitude. For example, 15 kilograms, or 10 pounds if it was money. Or if your speed, and speed, not velocity, because velocity we're going to come to, speed would be 15 meters per second. It is just a magnitude. We have not specified a direction at all. So some of the examples are speed, we've talked about time, 10 minutes or 2 seconds, energy, 15 joules, 100 joules, distance, 5 meters, 10 meters, and power measured in watts. All these we would describe as scalar quantities because they just have magnitudes. Okay, vector quantities, if you're a Despicable Me, if you've seen that film, you should remember there's a point where Vector says something along the lines of I'm committing crimes that have both magnitude and direction. So that's exactly what a vector is. A vector has magnitude, so a size, and also a direction. Okay, so for example, some examples of vectors would be velocity. So the velocity of 70 meters per second, we would have to specify the direction if it's a velocity. So we would say 70 meters per second north or south or east, etc. Weight, your weight, if you have a mass measured in kilograms, which is a scalar, when you are in a gravitational field and gravity pulls that mass down, you get a weight from it, and a weight is measured in newtons. It's a force, and it definitely has a direction, and when you're on a planet, it's downwards. Acceleration, based on velocity, so it's also a vector, and as we've mentioned, gravity would just bring gravity back in again. Gravity would be a vector quantity because it definitely has direction. Force, most forces measured in newtons, they are also vector quantities because they will have a direction associated with them as well as their magnitude. So vector diagrams, you must always not only show the magnitude, but an arrow shows the direction of the vector, and normally the size of the arrow is linked to the size of the force. So a large arrow will mean a large particular force or a large velocity. Okay, but all vectors must have an arrow or a statement of the direction of that the magnitude occurs in. Okay, so for example, some diagrams, a velocity diagram, you'd have to put an arrow with 50 meters per second on, so I can see straight away that's a vector. Weight, somebody's weight, 100 newtons downwards. Gravity is acting downwards at 9.81 meters per second squared. We'll meet that later on, the acceleration due to gravity. And a force, if you're pushing this rock, rather a large rock up a hill, you might be applying a 50 Newton force in the direction of the arrow. Probably won't do much to that rock, but there you have it. Okay, so do these people have the same vector quantities? Well, they don't, do they? Because they're both pulling at 20 newtons, which is the magnitude, but if you look, the person in the green t-shirt is pulling to the left, and the person in the red t-shirt is pulling to the right. Now, to differentiate between the left and the right, what we would normally do is involve a minus sign. So here I'm saying a minus 20 means to the left, plus 20 means to the right. And when you add these forces up, you would find there is no resultant force. So there is a resultant force of 0 because minus 20 plus 20 equals 0. We will do more about this when we probably talk about Newton's laws. Okay, some definitions of forces: contact and non-contact forces. This is very straightforward. Forces are normally pushes or pulls that act on an object due to the interaction with another object. All forces are either contact, so the objects are physically touching. So if you physically push or pull something, so if you put a rope on something and pull it, that's a contact force. If you place your hand against it and push it, that's also a contact force. But non-contact forces are where the objects are not physically touching or they're separated. So gravity is a good example. If you drop a rock or drop a stone, the earth does not need to touch the stone, it will pull it down because gravity is a non-contact force. And if you put two magnets together, if they're opposite poles, you should remember when you've looked at these earlier in school that they will repel or attract, and they do that repelling and attracting when they are not touching. Okay, so how are we going to add forces together when we've now looked at what we know what a vector is? Let's see what would happen if we added them up. So the first example, if we've got 8 newtons to the right and 5 newtons to the right, well, when you add those up, you literally just add up the sizes. So 8 plus 5 will give us 13 newtons to the right because they're both in the same direction. Number 2, because we've got 8 newtons to the right and 5 newtons to the left, we've got to take one as being minus, so you've got to add up 8 and minus 5. So if you did that, you'd end up with 3 newtons to the right as the resultant force. And finally, we've got 3 here. If we add 8 to the right and 2 to the right, that'll give us 10 to the right. Add on 5 to the left, that will give us 10 minus 5, which will give us 5 newtons to the right as a resultant. So these are the quite straightforward ones. You would possibly be asked to do this on 1 centimetre squared paper, and you could measure the lines, and it would normally be some sort of a scale that 1 centimetre equals 1 newton, and you might be asked to draw them out to scale. Okay, but fine, let's just make it a little bit more complicated. If the forces aren't actually along a line, so if we've got 4 newtons and 3 newtons, okay, now if this is on squared paper, what you can ideally do is you need to draw a line that goes 4 squares across and 3 squares up. Okay, so if you did that, that'd be 4 squares across and 3 squares up, and then if you measured this line would actually be 5 centimetres long if you were doing this on centimetre squared paper. If you weren't doing it on centimetre squared paper, you could use a bit of trigonometry on this, couldn't you? You might see that this is the 3, 4, 5 triangle. So you could say that 3 squared plus 4 squared, square rooted, will give you an answer of 5. So that's 3 squared 9 plus 4 squared 16. 9 plus 16 is 25, and the square root of 25 is 5. But with this on the specification, you may have to be able to cope with drawing these on to scale on squared paper. Let's do another one. We've got 5 newtons and 12 newtons. So again, we need a line that goes diagonally this way, and that diagonal movement of 5 up and 12 across will give us this direction. And from that you can see I could measure it, and if I measured this, if it was drawn on squared paper, this is 13 newtons long, or I could use trigonometry and do 5 squared plus 12 squared, square rooted, again just like last time. And this one here, a little bit more complicated. We've got 4 newtons and 2 newtons upwards, so added together those would make 6 newtons, and then 8 newtons across, so we need a line that goes diagonally across 8 and diagonally up 6. And again, I could just do some trigonometry and say 6 squared plus 8 squared, square rooted, or if it was on squared paper, I would physically be able to measure this line, and the number of centimetres would be equal to the number of newtons. Okay, so don't get confused. Just because these are distances and you're measuring distances, because it's all to scale, you can have you measure the length of a line, and that length of a line equates to an amount of force or a velocity or an acceleration. Okay, that's the main idea with vectors and using scale diagrams.